Thank you and welcome to OCX 2026 and welcome to the OCA track again. My name is Dana Vede. I've been working with the Eclipse Foundation since 2023. But before that, I've spent, well, practically my entire career in the automotive industry. I don't seem to be able to get away from this industry for some reason. And yeah, I've pretty much gone through all the software roles that you can imagine within a project. And eventually, I came to processes and to quality because I felt the need to bring everything together. The interfaces didn't feel like they were functioning properly between the teams. So that is how I looked more into optimization, into continuous improvement, and also that's why I'm here with the Eclipse Foundation, trying to bring more light towards the open source when it comes to standards and even more to safety for automotive. And with that said, after this too long introduction, I'd say, I'd like to ask for 3 volunteers from the audience. Nothing too dangerous or too spectacular. Carlton, thank you. Gentleman in red, thank you. I would, yes, please. Maybe we can have a 3rd volunteer as well. Come on, 3rd is a lucky charm. Thank you, Thilo. So I'd like you to state your first name and then to roll this wonderful dice that you can also maybe tell the public, and it has so many facets to it.
All right. My name is Carlton, and it looks like this is a 20-sided die. And I rolled lucky number 6.
Okay, please keep that in mind.
All right. Should I also roll it?
Yes, please.
All right. My name is Emilio, by the way. And that's 12.
Wow, that's a double. Thank you. Not that that would matter.
And I'm Thilo, and let's see what I get. You probably need to help me to read that. What is this?
That's a 10.
It's a 10, yes.
Wonderful. Well, thank you, all 3 of you, very much. I'm going to take that back to dice. And please remember those numbers, because I'm going to ask you about them towards the end of our presentation here. Thank you so much. And not to keep you in suspense and moving on, here's briefly the agenda of the talk that I'm going to give today. These are the main topics that we'll slowly be going through as we go through the presentation. As a first one, I'd like for us to set some foundations around functional safety, what it is, why is it good, and so on and so forth. So starting from the definition that functional safety is the part of the system's overall safety that relies on equipment operating correctly as a response to the inputs that it takes. Any problem with the statement? We all understand it, right? We all agree with it? Not so convinced? Well, at least this is what the standard itself says. And when I say the standard, I mean pretty much all functional safety standards that are derived from the generic one, the 61508. Now, to try to understand this a little bit better, safety is actually a claim. You know, when going back to the system overall safety, when we look at that, we want to make sure that the system has a precise and defined behavior whenever it encounters a failure. So at the end of the day, the success that could be drawn out of that would be ensuring that the system actually knows what it has to do when it encounters a failure. So if you want to make a parallel, for example, between C programming as a programming language and safety, the two of them are very similar. The C programming has certain behaviors that are not defined, but they are very specifically described. It would be similar for safety. A safe system would have all of its behaviors defined. It doesn't matter the type of failure that you encounter, the system has to be able to detect that and behave in a very well-defined manner as a response to that failure. Now, why do we think safety is good and is important? Well, we all drive cars, or majority of us. Even just from that perspective, you don't want to be involved in an issue of safety with your own car while you're in traffic, right? Let's say you're on the highway doing 60 miles an hour because you just entered, and suddenly something happens. I don't know. The airbag, the driver's airbag just pops into your face. That's a total no-no. You don't want that to happen to you, right? So that's why it's important. Now, reliability typically asks a different question than the actual functional safety. So it's more about, am I safe to use it and for it not to break? Am I sure enough that that system will not break? Well, for safety, the change is eventually it will break. And that's not such a big problem. The big problem is I need to be sure what will be the behavior if it actually breaks. And that behavior, as I said, needs to be properly defined. How is the whole thing helping people? Well, it mainly guards us against misbehavior, because as I said, if the behavior is well defined and properly implemented based on the potential failures that we could see in the system, then obviously we know how it behaves. A misbehavior would be that we encounter a failure, we know how we want the system to behave, and yet the system is not capable of exercising that behavior. We could encounter mainly two types of failures, at least in our line of work, which would be hardware failures. That could be random failures. Things like a sensor has gone beyond its expiration usage date, or because of that, the ranges in which it functions properly are completely haywire. But there are also systematic failures, which determine a lot of how the system overall should behave. And the systematic errors are usually related to designs and to software. I underline both of them because very often we see, especially in the automotive industry, that bad hardware design has a really huge impact on the actual software. So we suddenly have to do all sorts of tricks within the software to make up for a bad design in hardware. Such things need to be looked at very carefully because they can come with really big implications, especially if they are not properly documented. Now, in order for us to know, to establish, better said, this behavior of the system in case of such failures, we need to appeal to safety mechanisms. And such safety mechanisms would be, on one hand, making sure you have a secondary path. As an example, well, today all vehicles have two headlights. Why do you think it got there? The initial idea was to have one light. I need to be able to drive in the dark. So one light should have been enough. But because potentially the light bulb in that one headlight could have been broken like really easily, or maybe you have a short circuit in the electrical circuit of the vehicle, the light bulb could have gone off as well. That's why they came up with a secondary path, meaning a second light bulb. So it doesn't have to be something over-engineered, over-complicated, just giving the system a secondary route that it can take to even avoid a potential failure. And that really helps a lot, because by putting in place such secondary paths, we also figured out that we need to monitor the system. We need to figure out how it behaves. We need to let it self-diagnose. And those are actually the points through which we can ensure the secondary safety mechanism that is usually applied. Now, having such safety mechanisms in place permits the system, once it encounters a failure, to go back to a safe state. So, I don't know, let me think of an example. Let's use the IVI part for now. Let's say we are doing navigation. We are supposed to get from here to the hotel, to Marriott's, and at some point in the traffic, instead of directing us towards right, the navigation is directing us wrongly towards left. We notice that because we take the left and figure out that we're not getting where we're supposed to. So what would be best to do? To continue on that route until the navigation keeps recalculating and keeps rerouting us and so on? Or would it be best maybe to just stop and restart the navigation? Maybe the typical Control-Alt-Delete that does the trick. But the point is, once we do the stop or we change the parameters of that navigation, we are helping the system to go back to a safe state of operation. And that's the main thing for functional safety. Now, we talked about what safety is in general, but we should be framing it also into standards so that we understand why exactly safety is important for our industry and in general. Well, for the automotive industry, of course, probably all of you know that ISO 26262 is the main standard when it comes to functional safety. However, this standard was actually derived from the general one, the 61508. And as you can see, there's loads of other standards, and I've only mentioned a few of them here, that have been derived, all of them, from the generic one, the IEC 61508. I'll make a few references further on to the 61508. If you have questions around it, it's probably better to ask them now so we can clarify them before we enter those topics. Okay, hearing none, moving on. So looking into the actual safety standards, what we notice, especially looking in our automotive industry, we notice that there is a path towards safety, right? And how do we achieve that path inside of a project? Well, we start discussing what exactly is it what we want to create. Then we start laying out at least the top level requirements. Then we're going to start decomposing those requirements into smaller ones, potentially hardware, design, software, and so on and so forth. But eventually, what we're going to have to do is we're going to have to analyze the design or even architecture that we have in mind and try to identify potential problems, potential failures. We're looking for hazards. That's the main thing there. And a hazard, especially in our case, would mean like having somebody's life threatened, having somebody's health threatened because of that issue, or even having a property under threat. The simple fact that a vehicle catches fire on a highway while it's still driving, that's a really big issue. We don't want that to happen. So the whole point of doing this exercise within the project, applying the functional safety principles within the project is, as I said, starting from identifying the hazards, analyzing those to determine if there are really a risk. And then once those risks are identified, we start to look for ways to mitigate them. So we've established that there are real risks. We've established which of them can be mitigated, which cannot be mitigated, and also to what extent they can be mitigated. Because we'll never be able to mitigate all the risks. And this is where another topic comes into the picture, and we'll touch that a little bit later as well, called liability. So people in our industry in particular have thought, okay, I want to build a vehicle. The expectation, at least from my customers and potential end users, is that this vehicle is safe. Now, according to the standard, I gotta go through those steps, and I gotta analyze all the risks that I've identified and try to mitigate them. Based on those risks, I will know how much I'll be able to mitigate and how much I will need to cover through other means. And the reason for which I say cover is because usually the other means would be insurances. And these are put in place especially to support that liability factor of the whole picture. Now, in safety, we obviously we have a lot of rigor, but also this rigor is split in a few levels, let's say. Going from A to D, these would be the safety integrity levels. For A, you have the less rigor. For D, you have the highest rigor. I haven't mentioned QM, because, well, that would also be a qualification. But QM, that means quality managed. Meaning, from a safety perspective, there's nothing in addition for you to do than your typical software development, testing, integration, and so on practices. Nothing very safety, functional safety specific to be defined in there. And looking at those risks, the most important aspects to retain about those risks so that we can further on analyze and establish what we can mitigate and what further on needs to be covered by an insurance would be these three elements, these three factors: the severity, the exposure, and the controllability. So obviously, as we talked, the severity would be related to how dangerous that situation would be. Is my life going to be under threat? Is my health going to be under threat? I don't know, maybe I have all windows open, I catch an air draft, and my head hurts all day. Yeah, that's a health issue, which I caused by myself. So it's not really under this subject. I'm trying to explain we need to look at each of these cases one by one, understand what the technicality behind them is in order to determine what the actual risk it poses. The exposure, well, it depends how frequently it happens. How frequently do we encounter that particular dangerous situation? If it's, I don't know, I've recently seen an issue with a gentleman that had to take his car to the garage because every time he was turning the steering wheel to the left, the honk started to, the car was starting to honk, and it was really funny. That's not necessarily a safety issue for that guy in particular, but it could become a safety issue for the people around him. So for the actual traffic. Again, need to be careful how we look at these risks. And then last but not least, it's the controllability. So what is our ability to control that situation? Can I, as a driver, intervene so that I can make that failure disappear? It's a valid question. Can somebody else around the vehicle or within the vehicle intervene to make the situation better, to bring it back to a safe state? And again, once analyzing all these risks and, of course, all these three factors, we start to create this risk assessment matrix, based on which we'll determine what we can and should take care of, should mitigate, and what we cannot and needs to be covered through those other means. Going a little bit further into the actual engineering lifecycle and methodologies and maybe some practical examples of what this means in the real world. Well, from an engineering perspective, we've looked at the V cycle, and by God, I think all of us are sick and tired of it already. But the point is, this V model gives us the best way, I would say, to ensure that we start from requirements and go through all of the activities one by one, sort of like in a sequence. Now, the traditional way of doing this is to do it strictly in a sequence with no overlaps. But in the last years, I'd say 10, 15 years, or even more maybe, while looking at the agile methodology, people have tried to implement the two of them together. And I would say it's quite a good approach, and it functions quite well, as long as it's well established, well defined, and people understand what exactly it is we want to achieve through that. So bringing agile in this picture doesn't necessarily mean that we don't follow the same sequence. It just means that maybe I can start with my system design or my architecture design before I have 100% completion on the requirements. It's a thought to take into account. And that actually gets to be propagated further down. We're never going to have a full MVP just going through this V cycle once. Even if just for the sake of needing to make fixes for bugs. As we all know, there is no software with no bugs. There's just software that hasn't been tested enough. Those bugs will eventually appear. But again, they also depend on the requirements here. Those requirements also establish in what environment our final product needs to function. Whether it's a vehicle, like in our industry's case, whether it's, I don't know, even a watch that monitors your heart rate. That also has a safety function in there. Going further, you probably heard about SOTEF, or better said, 21448. This one is a safety for the intended functionality, and it springed its head through all of the other standards once we started looking at the feature, especially in the ADAS area. The point with those is we want to make sure that systems do not get confused by the information that they receive from outside, so from the surrounding environment. In the most recent years, we are very much linking that to AI. But it's not just AI. I mean, AI, at the end of the day, is yet another product of the human minds. It didn't just pop out there, right? We are the ones that created it. So it's still going to act, it's still going to behave the way we specified to it to behave. So don't consider that being just an AI-related thing, right? It might be that you've done the specification, but while you were doing the implementation, you got carried away with, oh, this is really cool. I've got yet another idea. I'm going to improve this even more. And then that's where your disconnect happens between the specification and the code. That's where the issues can pop. So having some specification, not necessarily 100%, before starting to write your code, has some sense because it needs to give you some direction to what you do. Now, when we look at safety case requirements, they can vary, and they can be of all sorts of types. They can be technical requirements, they can be standard-related requirements, they can be, hell, I mean, they could even be broken down into HR-related requirements. I need to have a functional safety engineer to work on my project. That's an HR requirement. It's not going to be the project manager hiring that guy or your customer hiring him for you. Similarly, there could be, I don't know, an additional requirement to follow, I don't know what, extra regulations for a given country. In case you missed that, usually it's each country's government that establishes what regulations they want to apply on their roads to keep them safe. Nobody really asks any OEM, bring me your certificate on functional safety so that I can open the door and let your vehicle go out there on our streets, on our public roads. It's more about this mitigation of the risks. So the government wants to ensure that whomever produces a functional safety related product, whether it's a vehicle, I don't know, a train, a medical device, knows what they are doing in the means that they've done absolutely everything that they could to make it into a safe product. And in case there are some risks that couldn't have been mitigated, they want to make sure that the respective producer can be made liable. Meaning they have a high enough insurance to pay for the damages that they potentially could create. And for the actual safety case, as I said, we're not looking just at technical requirements. We're making sure that we have a process in place. You can't do safety development with an ad hoc process. You can't just decide from one moment to the other, oh, I'm just going to skip testing altogether, like the lower levels of testing, and I'm just going to go straight to validation. You have to have a well-defined, well-thought process that also incorporates all these elements that make claims towards your future product. These elements that come from the said safety standards. So we're looking at processes, we're looking at validation, but one of the things that is, well, for all of us, hopefully, and not just from a safety perspective, really important, but also something that the assessors, auditors are always keen to ask for, is a traceability. When we say traceability, we mainly mean bidirectional traceability. So back and forth from your initial requirements, right, from here, to your vehicle, because of the implementation, and then to your testing side of things. Because eventually you'll also have acceptance testing, meaning that your customer will have to test your product based on their well-defined boundaries of the system. So traceability, why is this one so important for us? But again, hopefully not just from a functional safety perspective. As engineers, we learned that we solve things faster if we know where things are broken. So that's what traceability does for us. If something breaks down, having this full traceability, bidirectional traceability in place, helps us to faster detect the issue and come up with solutions for fixing it. One other thing that I want to talk about a little bit while we're on the standards themselves, it's not just the certification that is important, And obviously, the certification comes in after actually having an audit, after having an assessment. But it's making sure that, again, as I said, we have a process that is well-defined and is established. It's first of all the process that needs to be assessed to see, is this process really taking these guys developing this project in the right direction? Or is it taking them in a completely different or random direction? That's a first element that the assessors need to make sure, of course, after we ourselves have made sure of that too, because that was the initial intention. But then, after seeing that process, we also want to make sure that the process is properly applied in the project. We can't just claim, oh, we have a process over here, 50 pages, who wants to read it? It doesn't go like that. We really need to apply that, like on a daily basis, on a task base. It needs to become ingrained into the way we work. And last but not least, they will also be looking at the code. And when I say code, I don't mean just the code that gets to be executed on our vehicles. I mean code also part of the test scripts, for example. I mean code also scripts that potentially generate extra documentation for you. So they'll be looking at literally all the artifacts of your project, and they will come up with an answer. After they put everything in balance, after they make sure that you've specified all of the possible behaviors of your system, and also going to a safe mode of the system after encountering a failure, that's when they'll come back and say, it's a yay or it's an A. They won't give you too many details if it's an assessment for certification. If it's an audit, that's their duty, to provide you with all the feedback possible to help you improve what you've already done. And a little bit of a practical context. I'm pretty sure you all are familiar with all of these examples. First one would be the ABS module in our vehicles. As you know, that is very important, because if your brake doesn't function properly, we are screwed. There's the electric power steering. That's also very important, because it has to deal with the motors, and they need to disconnect the power in case they don't work properly. But we see things like this in other industries as well. Not too far away as, you know, the elevator that you probably took this morning coming downstairs from your room in the hotel. If one of those elevators malfunctions, more horrible things than just being blocked in it for 20 minutes could happen. It could just drop. And depending on the level where you start from and it starts dropping, it might become an actual issue. I mean, it could result in actual injuries or even death. But then there's also industrial cobots, which are those collaborative robots that use light curtains to cut off the power if a human is found in a working area where they're not supposed to be. So there's plenty of examples that we can look at. Maybe you've seen the latest Hoovers, the ones that are automatic, really round-shaped, tiny. They just walk around the house as they would be in their own world. Well, even those have some safety in there. If, for example, you have a toddler in the house and one of those vacuum cleaners steps on the baby's foot, what are you going to do? We need to make sure that it's safe for the baby, right? And that's just one example in that direction. So even household equipment can become dangerous if it's not properly designed and specified. Now, because we are at an automotive track, we'd like to go back to the SDV part of things. So let's talk a little bit about the challenges, the safety challenges in the SDV era. So we talked very little about the navigation, so the IVI module, but that one actually is part of a broader component within the vehicles these days, that component being ADAS. And the reason for which that component is so important is because while we're thinking about introducing more and more artificial intelligence all around us and in our daily work, our daily usage of products and so on, of course we'd like to put that stuff into the vehicles as well. Obviously, after we test it and we make sure it's safe, because we're talking about functional safety here, right? But the point is, it becomes more and more important to ensure that topics like functional safety and how exactly to achieve functional safety from a technical perspective and not so much from the stamp on the paper perspective is very important, because there will be more and more vehicles out there having more and more electronics in them, which means potentially even AI soon. And as end users, we want to be able to at least understand what we are making use of and how to look at those products, how to identify potential failures that maybe have not been specified, how to ensure that we are using them in the proper manner as they were specified to be used. I don't know, it might be familiar at some point about 15, maybe 20 years ago, there was this case in US, I believe. An individual bought an RV, and the RV in its book, it said that it has a sort of a co-pilot function. But the guy didn't want to spend too much time reading the manual. Who wants to read the manual? And from co-pilot, he understands literally, oh, I can just tell it what to do and it will do for me. Well, surprise, surprise, the guy set the cruise speed on the vehicle and thought that was it. So he went to the back of the RV to make himself a coffee. And guess what? He crashed in a rock, because nobody was watching the steering wheel, right? So we ourselves, as end users, also need to educate ourselves to understand what we are using and how we're supposed to use those products. So again, coming to the ADAS, there are all sorts of functionalities or features, as we've heard them in the past years, that are incorporated in this bigger component. Things like AEB, like lane assist, like cruise control, like ACC. All of these things have to be able to handle failures. So obviously, as we were discussing before, diagnostics is a must in this area. There cannot be any ADAS component without proper diagnostics dedicated for it. Otherwise, we'll not be achieving safety in that direction. It's just as easy as that. But is that enough? Isn't it maybe also about a little bit of discipline? Like we were discussing before, yeah, I'm writing down some documentation, but then I get caught up in what I'm doing, and it's so exciting, and I like it, and I haven't been coding in years, and I'm really excited about doing this, and I have really good ideas, so I'm just going with the flow, and at the end of the day, I'll be, I don't know, 50% off from my initial spec. Should I leave it like that? Or should I go back and update my initial spec? Or maybe even look at the code that I've written and pause a little bit and think about it. Is this really needed? Is this really what I wanted to make? So always making these correlations and maintaining that discipline of doing these actions is quite important, because discipline is also about processes, establishing them, first of all, defining and establishing them, making sure we're actually applying them, but consistently, not just on Fridays, because it's a shorter day. And it's also about, again, rigorous validation. When we say testing, just thinking about the IEEE standards when it comes to software development and testing, there are multiple layers or multiple levels, however you want to see them, for testing. Just the fact that I did the validation is not enough, because I might have a problem on the hardware side, I might have another problem on the software side, and guess what? Coincidentally, the two of them annul each other, and I'm not going to see anything in the validation. That's why it's really important to start really from the low-level things and make our way up to the top without skipping any steps in that testing phase. I know everybody wants testing to be instant, potentially fully automatable. It's not always like that. There are some things that we might need to test manually. There are some things that we might just test them visually, like they do in the plants, for example. So just keeping in mind that each test, each type of test, each level of tests has its own purpose, a very well-defined purpose, and that's why we need to keep this discipline around them. It's important, not just for functional safety, but software development in general. And last but not least, there are design phase decisions. Like we were saying before, okay, I got carried away with my coding because I'm so in love with it, I haven't done it in years, and wow, this is great that I can do it now. But is the direction the right one? Shouldn't I be going back and update my spec? Or is it really what I've done? Is it really that important towards my spec, towards achieving that product? Now, talking about, I have to close. Unfortunately, I didn't take enough time to go through the presentation with you. What I would like, obviously the slides will be made available for everyone. What I would like to go through though are some thoughts and ideas around open source and safety within open source. And there's mainly two ideas that I would like to underline. So you are probably familiar, or maybe not, with Linus's law. Linus, the creator of Linux. This law says that leveraging peer review for a faster bug detection and vulnerability patching is better than for closed systems. So that's one thing to really keep in mind, because it's really about open source. And the second one is there's a cultural mismatch, meaning that traditional safety is usually relying on proprietary or locked down code. And this is actually clashing with the idea of having a transparent, collaborative approach, the one that open source has. Now, the way to bring these two together is to start to see that, in fact, what's important is to have a safe, or as safe as possible, system, rather than having that stamp on a piece of paper. And this is what makes things like our approach for functional safety way better, I would say, in my opinion, because we have a big pool of reviewers, testers, coders. Those secondary pairs of eyes are quite plenty in the open source world. In the corporate world, this doesn't happen that much. Not everybody will have time to review your code or your design or your architecture and so on. So that's on one hand. On the other hand, I'd like you to mark this down in your head and go back to this slide and identify those things on our Eclipse Foundation website. So we have a number of processes like Eclipse development process, the Eclipse functional safety process. We have IP and security policies. We also have a very small SDV process. All of these taken together are practically replacing, at least for open source, all that heavy corporate style of processes that exist inside of corporations. And why? Because in the open source, the main thing is about collaborating and bringing everything out in the open, having everything transparent. And I'm really sorry, but I'm going to have to end here because we have the next speaker coming in. My apologies.
Thank you, Dana.